Hello, everybody. I wanted to make a video to show you how to do acid ionization calculations. So far, all the acid-base calculations you guys have been doing have been with a strong acid that completely 100% dissociates. Okay, they call that acid ionization. So let me show you what I mean by that. For example, we've looked at hydrochloric acid, HCl, putting it in water, and it's splitting apart into H plus and Cl minus, or the hydrogen ion and the chloride ion. 100% splits apart. That makes the math fairly easy because all you got to do is figure out how much of this you make, take the negative log of it, and you've got the pH of the solution. But what if it didn't all the way split apart? Okay, for example, what if you had vinegar this guy here, that's acetic acid, which is what's in vinegar. And I'm going to draw it this way with a little arrow going forward and a big arrow in the reverse direction, just to show you that most of it stays together. It's very reactant favored. And a little bit of it splits apart into H plus, that hydrogen ion, and what we call the acetate ion, which is CH3COO negative. Okay, so that's the weak acid. Now the calculations that I'm going to be showing you how to do today is how do you calculate how much of that will separate when I put it in water. Well, I'm going to show you how to do that. The good news is it's going to be using ice charts like you learned in the equilibrium chapter, but a little bit easier ice charts. Okay, and I'll show you. I'm going to share the POGIL with you so we can look at it together here. All right, here it is. Common ion effect on acid ionization. And remember, acid ionization is just how much of that weak acid is going to split apart, because that tells you how acidic. You can calculate how acidic it will be, what its pH will be, if you can figure out how much of it will split apart. And remember, strong acid 100% splits apart. Weak acids, only a smaller fraction splits apart. Okay, so that's what we're going to be calculating. And then you notice on this POGIL, they use ice charts, just like we learned in the equilibrium chapter. So we're going to be using those again. Look at the equation they wrote and see how it's different from mine. They wrote acetic acid here, HCH3COO, and then they wrote plus water to show you that they're putting it in water. And then they have just only a forward arrow, which I think they should use a reverse forward arrow like I did, because I think it's a nice visual to show you that it's a weak acid because it mostly stays together. And then they have for the products H3O plus instead of H plus, but it's the same thing. The H plus is in H3O plus. H plus is the hydrogen ion. H3O plus is the hydronium ion. But they're the same thing. It's just the H3O plus is showing you that water is holding on to the H plus. Okay, other than that, there's really no difference. And then they show you the acetate ion, CH3COO negative. Now, the way I wrote it is more of a net ionic equation, only the stuff that we really care about. Okay, for example, I didn't list the water that it's taking place in, because remember, when you do an ice chart, you only put down the things that are aqueous or gases, and there's no gases in this acid-base stuff. So really, we only care about the aqueous species in this whole equation. We know it takes place in water, so we don't have to write that down. Okay, and in the H3O plus, I just write it as H plus, because that helps you see that that's the measure of the acidity. If you take the negative log of that, you've got the pH of that solution. So we're going to go with the way I wrote it here, but then I just want you to know that they wrote it in a different form, but it all means the same thing. All right, look at their ice chart. They listed the HCH3COO concentration. I'm going to write ice right down here, just like they have it. Okay, concentration starting out as 1.0 molar for your vinegar or your acetic acid, and then they put it in water. Well, initially, you don't have any H plus, and you don't have any acetate ion. So there's 0 starting out. All right, I'm going to unshare for a minute so you can see full screen here. Here we go. Now, remember the law of mass action, products over reactants. We use the same law here. The K value, in this case, they call it Ka because it's the equilibrium of the acid is why they write it that way. Ka is going to be equal to my products, H plus, times my reactants, CH3COO minus, over my starting, my reactant, my starting molecule, my acetic acid, HCH3COO, HCH3COO. Okay, so it's just the law of mass action like you guys already learned. If there was any coefficients in the formula, we would take them to that power. And in these acid-base calculations, usually just a coefficient of 1, so you don't have to worry about exponents with these, which is kind of nice. Okay, and now after you get it written in this form, you just start plugging in numbers just like we did before. Okay, let's go back to our ice chart. So we started out with 1 molar HCH3COO, or acetic acid. It's going to change by X amount. That's what we're trying to figure out, how much of it's going to dissociate. And at equilibrium, it's going to be 1 minus X. Now my H plus started out at 0, but it's going to change by plus X amount, and so is my acetate ion. Okay, so they're both going to be X. I didn't leave myself enough room to finish my ice chart here, but they're both going to be X amount at equilibrium. All right, so the next step is just to start plugging in numbers into your law of mass action. So we know the Ka value, they give it to us in the problem. Let me reshare that with you here. The Ka value, see it right here, is 1.76 times 10 to the negative 5th. That tells you right there that it's a weak acid, because remember in the equilibrium chapter, when we talked about K values, we said if the K value was greater than 1, then the reaction was very product favored, which would mean in this case it made a lot of acid, it made a lot of H plus. If its K value is less than 1, it's very reactant favored, meaning it would stay together more. Well, this is a small K value. It's 1.76 times 10 to the negative 5th. I'm going to write it right here. That tells me a couple of things. It tells me that it's a weak acid because it's got a small K value, which means it's very reactant favored, which means most of it's going to stay together. Okay. It also tells me when I do the math for this, I'm going to end up having to take the square root of this number. Okay. Let me show you why that is. When I plug in X here and X here, because that's what the equilibrium concentration is of those two guys, and I multiply them together, I'm going to get X squared. Now on the bottom here, it's going to be 1 minus X. But just like in the equilibrium chapter, we don't want to do the quadratic equation. And we can get away with not doing it in this case, because remember our range, if it's 10 to the negative 5 or smaller, or if it's 10 to the 5th and bigger, you can ignore the X, the plus or the minus X in your formula. It's going to make you have to factor and use the quadratic. So in this case, it's smaller than 10 to the negative 5th because it's 1.76 times 10 to the negative 5th. So therefore, we can ignore this minus X right here. Okay. And that's typically the way it is with these formulas, these ice charts. And when you're doing acid ionization of weak acids, typically that's how these turn out, which is nice. It makes the math a lot easier. Because what it all turns out to be is that the Ka value is equal to X squared. Okay, if we're starting out with 1 molar, that means I'm just dividing by 1, which doesn't change it. So all I have to do to solve this, to solve for X, remember I want to know what X is, because that's going to be how much acid it releases, how much H plus it releases. It's also going to be how much acetate ion. So once I know X, then I can turn back around and plug it in, and I can figure out all these guys' concentrations at equilibrium. Okay, it'll be 1 minus X for my acetic acid, and it'll be X for my hydrogen ion and X amount for my acetate ion. So to solve for X, all I got to do is take the square root of the Ka value. And that's usually how these work out. So I'm going to plug this in my calculator here. Okay, I'm going to plug in the Ka value. It's 1.76 times 10 caret negative 5. And then I'm just going to hit the square root button. And I got 0.00419. Okay, or I'm going to round that to just 0.0042. That's X. 0.0042. Okay, so that really should all be reviewed for you. We've done those types of equations in the equilibrium chapter. Here's what's new in this. I'm going to scroll down a little bit here on this POGIL. See this percent acid ionization that they're going to have you calculate? That's the percent of it that's split apart. And remember, acid ionization is how much of it's split apart. Well, they want to know what percent of it's split apart. Well, what you got to do is you got to take X, that's the part that's split apart, just like any percent, and divide it by the total. Okay? And remember, our total, our starting amount was 1 of our parent acid. Okay, so 0.0042 divided by 1 is just 0.0042, and then you multiply by 100 because you're doing a percent acid ionization. Well, that's just moving your decimal 2 to the right is all it's doing. Okay, if you take 0.0042 times 100, it's 0.42. So the answer to that, the percent acid ionization of this, is 0.42%. Okay. What does that all mean? What that means is if you take 1 molar vinegar or if you take 1 molar acetic acid and you put it in water, only 0.42% of it is going to make H plus ion. That's why it's a weak acid. That's what you just calculated. Okay. All right. One more thing I want to show you here, and then I'm going to let you guys work your way through this POGIL. And by the way, it's very easy to just go on the internet and pull up these POGILs already filled out because everybody in AP chemistry uses them and they're all over the internet. But I don't want you guys to do that until you try them. Okay? I don't mind you looking them up to see if you're doing it right. But you got to try it first because when we take the test over this material, you won't be able to just pull it up on the internet. You're going to have to be able to do these calculations. And these calculations aren't hard. They're not as bad as the equilibrium chapter when we had to do them in that chapter when you were first learning them. These will come back to you a lot quicker, and they're pretty simple to figure out because it's just taking square roots and plugging numbers back in and doing percents. Okay, let's do Beaker 2. Let me just share you that one because there's something different about Beaker 2. If you notice, for Beaker 2, they're starting out with a little bit of the acetate ion already in initially. Before they even added the acid to the water, there's already some acetate ion in there. Maybe they threw a little sodium acetate in there. We don't care about the sodium because it's a spectator ion, so they don't even list it. Now let's review. You've done these before too. Let's review one of these real quick. HCH3COO, splitting apart in water to make H plus and CH3COO minus. All right, there's our formula. Okay, now when we do our ice chart, they're telling us we're starting with 1.0 molar vinegar, 0 acid, because they probably threw sodium acetate in there, and 0.2 molar here, okay? All right, now we've got a little bit of an issue because we're going to end up with a plus X and a minus X that we're going to have to ignore in this case. All right, so let me show you how to do that. The change is we're going to lose X amount, we're going to gain X amount, and we're going to gain 0.2. Well, actually, we're just going to gain X amount here too for the change. So it would fill in like that, just gain an X amount. But now when I do the equilibrium row of my ice chart, it's going to be 1 minus X x and 0.2 plus x. When I plug that into my law of mass action, it's going to be 1.76 times 10 to the negative fifth equals x times 0.2 plus x over 1 minus x. All right, that's going to be some crazy factoring and foiling and quadraticing math to solve for x. So what are we going to do? Well, because it's such a small Ka value, we're going to ignore the plus x and we're going to ignore the minus x. Okay. Did I do that right? We ignore the plus x. And so basically, it's 0.2x. It's going to turn out 0.2x. So now what I got to do is I got to take the Ka value right here, and I have to divide it by 0.2. And that's going to be my x value. And then I got to divide that by 1 and multiply by 100 to get my percent ionization value. Okay? All right, I'm going to let you guys try that. Go ahead and work these problems through this POGIL, and then you can check your answers so that make sure you know how to do this. Because remember, in a few months, you guys are all going to be sitting in a college chemistry class. And our goal in all this is just so that you can, when you do into a college chemistry class, you'll be able to keep up. You'll know what's going on. You'll have seen this stuff before. Come back to you a lot faster, and you'll be successful in that class. All right, good luck.